Yeah, sure. Okay, so a lot of it is sort of like conceptual, but yeah, I will have all the talk notes. Like this is like a note outline posted to Google Classroom. Like on Google Classroom, you can find so we've had 9 other talks that had notes, and they're all there, and then you can all see them.
Will you post it before you give the talk?
Sure, I can post it right now.
Okay, because I want to like print it out and then I can take notes on the iPads and have like a plan.
Sure. Yeah, I normally print them out before the talk begins, so like people can see it. And also, if we have other activities like measuring pH, they can just get a brief summary of what they specifically drawn. But I forgot to print things out too, which is pretty sad. Okay, so atoms in motion. So do you guys know Richard Feynman? He's a scientist. So in his Feynman lecture, in one of his lectures they gave there are something called the Feynman lectures, which are very famous. They are the lectures given by Feynman when he taught the introductory physics class at Caltech. And so the first chapter is about chemistry, really. It's about atoms. He says so chemistry really is just sort of the study of dealing with like the constituent matter, like of molecules and atoms, and producing them and reacting them and such and such and such. So he talks about atoms. So atoms in motion. So we all know all matter is made out of atoms, of course, except for the things smaller than that. But they form atoms. And he says the most important info about the world they can give to one sentence. If he asks if there was one thing that we could keep to future generations and all knowledge is lost, what would be the most important? And he says, he being the preeminent scientist in the world, second to Einstein, so the greatest American scientist, at the very least, generally agreed, is that it's the atomic hypothesis, that being the most important sentence. And that is, if I can hold my phone, all things are made of atoms, little particles that move around in perpetual motion, attracting each other when they are a little distance apart, but repelling each other upon being squeezed apart. And that one sentence has a huge amount in it. It contains like electromagnetism and all of those things. And the thing to think about atoms is that they're sort of in a constant motion and they're wiggling. And that wiggling is heat. Like temperature is just the average kinetic energy, right? So like 1/2 mv squared is the average of the particles in the system, right? So heat is the energy of those particles, and it is described as translational and rotational motion. So translational motion is what you would normally think is like when you move along the x, y, z direction or diagonal or whatever. Rotational is when you're in place and you're sort of like rotating around. So that motion constitutes heat. And so really from an understanding of atoms, you can gain greater understanding of all the concepts that you learn in chemistry and such. So, for example, when you drop a ball, right, you know how it goes. It has a sort of it's like a spring-like motion, right, where it just sort of bounces and falls and then stops, right? The thing is, where is that energy going? Does anyone know where that energy is going? Very specifically. Yeah, but very specifically how? Like, what does that mean? What does it mean that it's converted into heat? Yeah. Or sound. Friction. Sort of. So, what's really happening is that when you have the ball hitting the table, its atoms are hitting the atoms of its table and are transferring its kinetic energy into the table. So it's now lost energy. So it bounces up, down, and goes down and down and falls. But the energy is conserved. It has to go somewhere, and it goes into the table. Now those molecules on the table are jiggling or wiggling a little more than they were before, and it's a little hotter. Like if you, yes?
Professor Ruan, isn't some energy lost as sound and others?
Yes, some is. So what really is sound? So sound is really, it can be thought of as like some sort of the wave of compression and like end of traction, right? So what that is that's just molecules that are moving forward, making the other molecules moving forward and then bouncing sort of back, right? So that's sort of really what sound is. It's all dealing with the atoms moving itself. That's why there's no sound in space. There's no atoms to move, right? So that's really what sound is. And sound is not some microscopic quantity that, or something like light. It is the movement of atoms, very specifically. Yeah. So we see this in introductory chemistry classes with the pressure, right? So force over an area is pressure. Pressure, the standard SI unit is Pascal. So that what that represents is Newton over meter squared, right? So it's the force exerted in an area. What that means, so where is my, there it is, okay. Oh, and this will go in later. I think I'll just go a little bit, no, I'll go over that later. Okay. So pressure would be force over area, right? So yeah, pressure is like force over area. It's like a pretty basic concept. If you have a larger area with the same force, you have less pressure being exerted on the general area. That's pretty obvious. Now, I have a question for you. We all know that when we compress things, it gets hotter, right? But why? Why does it get hotter? Yeah?
Because of the ideal gas law.
Are you sure? Are you sure about that? So let's look at that. Pivner. So this is like the first thing you learn in introductory chemistry. Pivner, which is pressure times volume equals the moles of gas times gas constant.
No, but PV stays constant, so temperature would have to stay
Yeah.
constant as well.
It can also change too, but
No,
like
V is
let's say
constant.
pressure is constant. If we have the volume, shouldn't temperature also have? Shouldn't it get colder if we compress it? Like what's going on here, right? Because if like this is 10 and this is 10. Right, and we have the volumes, now it's 5. This side still has to be 5, so we have to make the temperature lower. So why is it that when you compress things, it gets warmer?
Like the molecules are hitting each other more often?
Why would they do that? Yeah.
Because it's also increasing pressure along with decreasing
All right,
volume.
so so what's happening? How is it increasing pressure? Really?
By just pushing the molecules closer together.
Yeah, but does that increase the temperature? So with an increased pressure, there are more molecules hitting the wall, so we register more force, because now there are more molecules hitting it. But the average kinetic energy of the molecules is still the same. They're still moving at the same speed. Yeah.
Well, I was gonna say, because they have less space to move in, so.
Yeah, but they still have the same average kinetic energy, so the temperature should be the same.
Well-
Yeah, I know. I already talked about this a little bit with you. But
When you
yeah.
press.
I think this is all a conspiracy theory, and the temperature actually stays the same.
Okay, wait. So if you compress it, are you like putting force in there?
Okay, so you actually hit it on the head. Okay, so when you're compressing something, you're doing work on the system. Like if you imagine a container with the one wall being the piston. As it's pushing it down to compress it, the molecules that are bouncing around it hit the piston, and then the piston imparts energy, added kinetic energy to the molecules. That's why when you compress something, it increases temperature, because heat's being added from the piston, which is increasing the kinetic energy of the molecules. Again, everything based on the atoms. And so that's really what's happening. So if you just have a capsule, and you like transport all the molecules into one half and then transport the wall to 1.5, the temperature doesn't magically double. People generally think if you just shrink the volume, then the temperature should increase, right? But the temperature source is not from the volume or the shrinkers or whatever. It's from the work being done by pushing it. So that's really where it's from.
But then, wouldn't it be a little bit misleading to say that the increase in pressure is what causes average kinetic energy to increase? Because there are other ways of increasing the pressure in a system without changing the volume.
Yeah.
So, for example, if we add more gas molecules, or if we add more gas into a system that has the same volume, then wouldn't the pressure increase?
Yeah, the pressure.
But then the temperature would increase. It's
Yeah.
just adding more gas molecules
Or would
is
it-
not
Temperature would
imparting work onto the
Pressure.
system. So I think it's a little bit misleading to say that the increase in pressure is
Yeah.
always increases temperature.
Yeah.
If the increase in pressure is more of a result of putting the work into the system.
Yes. Also, though, there is another way, because we also know if you have put a very high pressure onto something, as it heats up, right? But that also, again, is just with the piston. So, like in the Earth's crust, right, you just have like a huge force pushing down on it that is pushing the atoms and giving them a stronger kinetic energy. And you're laughing for some particular reason. I don't know why it is, but what is it?
You're
Good
doing
for us.
Jeez, we're trying to record.
Okay.
No,
No, that's fine. Don't care about it. Anyways, so that's the real thing. So another way to think about atoms in the world is you can think of a liquid. Like what actually happens there? Just think about it in terms of the atoms and the molecules and the intermolecular forces. You might not have learned intermolecular forces, but they're just basically attractive forces between atoms. It's why water has cohesion, the hydrogen bond in between and such. That's one of the intermolecular forces. It's the strongest, I'm pretty sure. So, okay, so imagine your cup of water, okay? So you have your water molecules bubbling around doing their thing. And then the gradient, the distribution of the kinetic energy of the particles in the water is not like completely static. Like all the particles in any sort of object don't just have the same speed. They have a distribution. Generally, I think, where's my marker? There's my marker. Okay. Generally a normal distribution. So if you know what a normal distribution or a Gaussian distribution is, it looks like this. It's known as bell curve, right? So that generally is how the distribution of, so, okay, what is this? Kinetic energy, I don't know, molecules, one molecule, I don't know the extra. But you get what I see, right? Some molecules have less energy, some have more, and such and such and such. Oh, this is kinetic energy. This is the population, how many of it have that. So, in your cup, what is evaporation? Does anyone know what it is? It's very simple. Like, what is evaporation?
Evaporation from the surface.
Yeah. What is it?
It's
Water
like,
changing physical states.
Not
Yeah,
quite, because the molecules themselves don't like change into like solid or gas. That's on a macroscopic scale. What really happens? When we're talking about phase changes in a large scale, we're really talking about the processes of atoms and molecules, the focus of chemistry, through interactions between molecules. Yeah?
I think so. It's when you have that atom gains enough
You
energy
plug in your
to
computer.
escape from the intermolecular forces
It's
pulling
not
it to the other
Yeah.
atoms.
Yeah, that's what it is.
If-
When the molecules have enough energy to escape the liquid. That's why when you heat something up, it evaporates, or evaporates more quickly, because more of those molecules have the required energy to escape. They're wiggling strong enough in the crowd to escape. And so, yeah,
Like, so basically, if you add energy, it has enough like energy
to escape.
break the bonds.
Yeah, break the intermolecular, the bonds, yeah.
Exactly.
I think it's also important to say that, first of all, evaporation